Welcome to the Deep Dive. Today we're diving into the really fascinating history of how Google built its massive information retrieval system.
Yeah, and what's amazing really is how those early challenges they faced are still, incredibly relevant today.
Exactly. Especially in AI, right? Things like Retrieval-Augmented Generation, LLMs, generative AI.
hmm
It feels like the problems they solved back then are cropping up again.
For sure. Think of it as the origin story for some of the biggest questions in modern AI. We're drawing a lot from a really key talk Jeff Dean gave back in 2009 at WSDM.
Ah, Jeff Dean. Google legend, right? Focused on those huge, large-scale systems.
That's him. So this isn't just history for history's sake. It's about understanding let's say, the core engineering DNA that still shapes how we handle massive amounts of information, especially now that it's powering sophisticated AI.
So our mission today is basically to unpack those early Google search design principles and, importantly, connect the dots to how modern AI systems actually work.
Right. We want you to get a clear picture of how the past really informs the present in this, well, super dynamic tech landscape.
Okay, let's jump in. So back around 2009, what were the big engineering headaches? What defined the challenge of building these huge systems at Google?
Well, it was a mix of things, all kind of feeding off each other. You had the sheer number of documents they wanted to index, astronomical,
Billions, right?
many billions. Then the number of queries per second hitting them, huge. Plus, they needed to update the index constantly, keep it fresh.
And users expect answers instantly.
Exactly. Sub-second latency. And you needed to store quite a bit of info for each document. And the algorithms themselves had to be super efficient.
It wasn't just adding these things up, it was more like they multiplied the complexity.
Precisely. When the numbers are small, it's manageable. But when you're talking billions of docs, hundreds of thousands of queries a second, near real-time updates, the complexity just explodes.
Right.
And a really crucial metric they always watched was performance per dollar, getting the most bang for their buck from the hardware.
Can we put some numbers on that? You mentioned the growth between, say, 1999 and 2009. That really shows the scale.
Yeah, absolutely. So Jeff Dean joined mid-99. Back then, the index was maybe tens of millions of documents.
Okay.
By 2009, many billions. That's like 100 times bigger.
100-fold, just
Like
answering
queries per day. Even crazier, something like 1,000 times more.
a 1000x increase.
Yeah. And they were storing more info per document, too, maybe tripled that.
Okay, so bigger index, way more traffic, more data per item. What about speed? Like how fast could they update and how quickly did you get results?
The update latency improvement was incredible. They went from updates taking, a month or even longer
Right.
to getting some pages updated in just minutes. That's like a 10,000-fold speed up.
10,000 times faster updates.
And query latency, the time it took to get you an answer, actually went down despite all this growth from under a second to under zero point 0.2 seconds. So like 5 times faster for the user.
That's amazing. But hardware improvements like Moore's Law alone couldn't have covered that kind of scaling, could they? Dean made that point, I think.
That's absolutely critical. The growth in documents, queries, update speed, it just dwarfed what hardware alone could deliver.
The software was key.
Totally. It highlights how vital software innovation and, frankly, ingenious architectural design were. They couldn't just throw money and hardware at it. They had to fundamentally change how the system worked.
Which really echoes today, doesn't it? With AI models, sometimes the hardware isn't the only answer. You need smarter software.
Exactly. And he also pointed out that a design that works fine at one scale might completely fall apart if you try to scale at 10x or 100x.
Meaning you often have to go back to the drawing board.
Right. You hit fundamental bottlenecks. Just adding more machines linearly doesn't always cut it. You often need totally new data structures, new approaches. That constant evolution is just part of the game for large-scale systems. We see that in AI, too.
And the idea that they could swap out the entire back-end system without users noticing anything, that's just incredible engineering.
It really is. Testing on a small slice of traffic, having rollback plans, it speaks volumes about how sophisticated their setup was.
Okay, so given these huge scaling issues,
Yeah.
what were those really early fundamental architectural choices they made? It started pretty humbly, right? At Stanford.
Yeah, the famous story of using scavenged machines. Resourceful, you might say.
Definitely.
But even then, they knew the index would get too big for one machine. So right from the start, the plan was distribution, spreading the index, spreading the work across many machines.
Distributed computing from day one.
Absolutely, a core principle. And that's foundational for, how we train and run big AI models today, too.
So when they decided to split up, or partition, the index, they looked at two main ways, by document or by word. Can you break those down?
Sure. So partitioning by document means each piece, each shard, holds all the info for a specific chunk of documents. The good thing is, each shard can handle queries on its own, more or less. Makes it easier to store stuff like page rank for each doc, and network traffic is relatively low.
But the downside?
The big one is disk seeks. If you have a query with k words and n shards, you might end up doing OK times n disk lookups. That gets slow fast as n grows.
Right.
Plus, every shard has to look at every query, even if it has none of the words.
Okay, so that's by document. What about by word?
That way, each shard holds data for a subset of words across all documents.
Yeah.
So a k-word query only needs to hit, ideally, k shards. Much fewer disk seeks.
Hey, sounds better.
Well, the catch is network bandwidth. You need to pull info about matching documents from lots of different machines and stitch it together. It needs way more network capacity. And storing that per document info gets trickier.
And Google, back then, network bandwidth was the tighter constraint, so they went with partitioning by document.
Exactly. The trade-offs in their specific setup pushed them that way. And that early focus on scaling document info independently, you see echoes of that in managing context for archive systems today.
Interesting connection. And following that choice, they introduced DOSIDs, document identifiers.
Right. And a clever trick was assigning smaller IDs to more important, higher quality documents.
Why smaller IDs for better docs?
It enabled early stopping. When processing a query, if they found enough good results, meaning results with low DOSIDs early on, they could stop searching the rest of the index shard.
Ah, latency optimization. Assume the best stuff came back first.
Pretty much. A crucial way to keep response times low.
Okay, then you had the index servers and the dog servers. What did each of them do?
So index servers took your query and spat out a ranked list of score and DOSID pairs. They were partitioned by DOSID, replicated for capacity.
And their cost scaled.
With the number of queries times the total number of documents, that product gets big fast.
Okay, and dog servers.
They took a DOSID and the query and generated the title and the little snippet you see in results. Also partitioned by DOSID, but their cost scaled only with the number of queries, much less sensitive to index size.
So naturally, most of the optimization effort went into the index servers because their costs blew up as the index grew.
Exactly. That was the main performance bottleneck. Making those index servers fast at sifting through billions of documents was the name of the game. That focus on efficient retrieval from huge data sets is, again, directly relevant to RAG needing fast context lookup for LLMs.
Right. Okay, so moving on through time, 1999 to 2009, that corkboard era, the cookie trays with motherboards.
Yeah, a great image of early scrappiness. They moved to more standard hardware pretty quickly, though.
But even then, the 1999 system added important things like replication, ads, and crucially, caching.
Caching, yes, fundamental. They cached results from the index servers, those DOSID lists, and also the snippets from the doc servers.
And how effective was it? What were the hit rates like?
Not super high like a CPU cache, maybe 30 to 60%, but the impact was huge. A small number of cache machines handled a lot of the load, taking pressure off the backend servers.
Lower latency for cache queries, too, I bet.
Definitely. And interestingly, the queries that got cached were often the expensive ones, common words, popular phrases that hit lots of documents, so it selectively helped with the hardest queries. Again, caching common context is vital for RAG performance.
But caching has downsides, too, right? Cache flushes.
Oh, yeah. When the index updated or they cleared the cache, you'd see these big latency spikes and capacity drops while the cache refilled, something they had to manage carefully.
Makes sense. And alongside the serving system, the crawling and indexing were evolving, too. Started as a simple batch process.
Pretty much. Start with some URLs, follow links, queue new ones, stop when full. Sounds simple.
But I imagine crawling the whole web had challenges.
For sure. How not to hammer websites. Which pages to crawl first. Managing that massive URL queue, dealing with machine failures during a long crawl, lots of tricky bits.
And the early indexing. Also batch, using basic tools.
Yeah, standard Unix tools. A big pain point was lack of checkpointing a machine failure could mean redoing a lot of work. And the memory.
Ah, the adversarial memory, because they didn't have ECC or parity.
Exactly. Data corruption was a real issue. They had to build file systems with checksums just to detect it.
And updates were infrequent back then.
Yeah.
Like monthly.
Roughly. And it was this whole dance. Take replicas offline, copy the massive new index over. They even optimized to use the faster outer tracks of the hard drives. then switch traffic.
Wow. They also had something called the pair cache.
Yeah, and early optimization. If two words often appeared together in queries like New York and pizza,
Okay.
they'd pre-calculate and store the list of documents containing both words,
Wow.
kind of pre-intersecting the posting list for common pairs. It
Wow.
sped up those specific queries.
Clever. So early 2000s, index size and traffic are just exploding.
Yeah, index grew 20x, traffic maybe 20% month over month sometimes. Huge pressure on the index servers.
Needed constant software improvements just to tread water.
Pretty much. 10–30% improvement every month, on top of adding more hardware. The basic approach of adding more shards worked, but only up to a point.
Because making shards too big was slow or didn't fit on one machine.
Right, so the number of shards just kept growing linearly with the index size. They did get better at disk scheduling, but the real breakthrough was rethinking the index encoding.
The initial simple format wasn't cutting it anymore. They moved to a block-based format.
Correct. Much smarter. It grouped related info into blocks. Each block had a header saying, basically, this block covers docs from X to Y and how long the block was, allowed the system to skip whole blocks it didn't need.
Faster skipping. And inside the blocks.
They used bit-level compression. Things like Rice coding for doc AD differences, Huffman coding for hit positions, standard compression tricks but applied cleverly.
And the result?
Saved about 30% space, which is great, but often it was faster to decode too because you processed less irrelevant data. Efficient encoding is still huge in AI for model compression and fast data access.
But even that wasn't enough, right? The growing number of shards was still making queries expensive, which led to the in-memory index in 2001. That sounds like a massive shift.
Huge. Fundamental change. Instead of disk, the entire index lived in RAM across many, many machines.
Oh.
They repurposed replica machines to hold pieces of the index in memory, creating microshards. A single query might now hit thousands of machines. Needed smart load balancers.
Thousands. What were the benefits of going all in on memory?
Massive throughput increase, and latency dropped dramatically, especially for those really slow tail queries. The example was Circle of Life went from seconds and tons of disk I/O to being way faster.
Like 10,000 times faster access times, effectively.
Something like that. It really shows how moving data closer to the compute can give you huge wins. Still true in AI.
But new problems emerge, I assume, hitting thousands of machines.
Yeah, increased latency variance. A slow machine anywhere could impact the query. Even random background tasks, like cron jobs, suddenly mattered more.
And availability. Fewer full copies.
Right. Worries about queries of death taking out many servers, or data being unavailable if a machine died. They mitigated that by replicating important docs more heavily. This was also when Google started building its own data centers.
Taking control of the whole stack. Okay, then 2004, another design evolution.
Yep, generalizing the in-memory lessons. More flexible query distribution, central management, cleaner APIs so other teams like Book Search could plug in custom scoring, and heavy reliance on GFS, the Google file system by then.
And another new index format, a single flat position space.
Right. Instead of doc-AD positions within doc, it was just one giant list of all word positions across all documents. Had separate structures to know where docs began and ended.
What a change.
Needed super compact, super fast to decode, lists of positions, using delta encoding, storing differences. They looked at various ways to encode these deltas, variant, length encoded variant, but landed on group variant.
Group variant, how'd that work?
Okay, it encoded 4 delta values together in a bundle, 5 to 17 bytes long. The first byte was key. It told you the lengths of the 4 values that followed.
Like a little table of contents for the bundle.
Exactly. And that first byte was used as an index into a tiny 256-entry lookup table that gave the exact offsets and masks to pull out the 4 values really fast.
Why was that faster?
Less waiting around. The decoding steps didn't depend on each other as much, so the processor could do more in parallel. Significantly faster decoding. Again, this obsession with low-level efficiency. Vital for performance.
Amazing detail.
Yeah.
Okay, 2007, universal search. Big user-facing change.
Huge. Integrating everything web, news, images, books, video into one result page.
Meant all those different systems had to handle web-scale traffic and be fast.
Yep. And they built an indexing service so teams could get their data into the main index easily. The big shift was, instead of guessing which silo to search, web images, just search everything and rank the results.
Query all, then rank. Sounds more comprehensive, but way more demanding. Like integrating diverse data for AI now.
Good parallel. And around then, the push for low latency updates got serious. Minutes, not months.
Going from batch to near real time. That must have been tough.
Massive undertaking. Redoing the whole pipeline. Figuring out what changed, crawling it fast, getting global info like page rank updated quickly, serving systems handling constant updates. Complex stuff. Again, very relevant to keeping AI knowledge fresh.
And through all this, being able to experiment easily was critical, right? For improving ranking.
Absolutely essential. They built tons of internal tools and infrastructure just for that. GFS for storage, MapReduce for batch analysis and data prep, Bigtable for fast online lookups of per-doc info needed for experiments.
That infrastructure sounds familiar, foundational for a lot of big data and AI work later.
Totally. Their experimental cycle was rigorous. Offline tests first, latency not key, then live tests on small traffic slices, latency critical, then tune and roll out, always balancing quality versus cost.
Okay, so let's make that connection explicit. How does all this history, these challenges and solutions, directly map onto what we're doing now with AI RAG, LLMs, Gen AI?
The parallels are really striking. Take scaling. Google wrestled with web-scale data and queries. Today, training LLMs needs massive data, and RGAIN needs efficient retrieval from huge knowledge bases. The scale problem is fundamentally the same.
Just shifted domains. What about indexing and partitioning?
Still crucial. ARG needs fast access to relevant context for the LLM, how Google sharded its index. Conceptually similar to partitioning vector databases or knowledge graphs for AI, those old debates on how to partition, they're echoed in how we structure knowledge for AI retrieval now.
And the need for low latency retrieval. Fast search results then. Fast context retrieval for RAG now.
Exactly. Users expect fast AI responses. That means the retrieval step in ARG has to be lightning quick. Sub-second is often still the goal, just like in web search.
Do those encoding tricks like group variant matter for AI?
Definitely. Saving memory, speeding up access, vital for LLMs. Efficiently encoding vector embeddings or knowledge graph data uses similar principles to Google's index encoding. Faster retrieval, less resource use.
And the continuous updates problem. Keeping search fresh versus keeping AI knowledge current.
It's the same challenge. The world changes constantly. How do you keep the information your R&D system uses up to date? Google's struggle with near real-time indexing foreshadowed this need for freshness in AI knowledge bases.
And the focus on experimentation and infrastructure seems universal.
Absolutely. Rapid prototyping, solid evaluation, iterative improvement, all built on scalable infrastructure. That's how you build complex systems, whether it's search or AI. The lessons from Google's infrastructure are directly applicable.
Finally, that universal search idea, one place for all info, seems like the goal for AI too, integrating knowledge from everywhere.
Excellent point. Breaking down silos, providing unified access, it's a common thread from search evolution to modern AI ambitions.
So really, a lot of the foundational work for building Google Search provided the playbook for tackling similar challenges in generative AI today.
Precisely. Those old problems, scale, speed, efficiency, they haven't gone away. They're just showing up in this new, exciting context of AI. The engineering ingenuity from back then is directly informing how we build these new intelligent systems.
It really makes you wonder, doesn't it?
Yeah.
As AI gets even more complex, integrates more real-time data, how will the next generation of information retrieval adapt? What new partitioning, indexing, or encoding ideas might emerge building on these foundations?
That is the big question, isn't it? How do these fundamental principles evolve for the next wave? It's fascinating to think about.
Definitely food for thought. If you want to dig deeper, Jeff Dean's original talk and the related papers are really worth checking out for more detail on these engineering feats. Thanks for joining us on this deep dive.